Hi everyone. In this video, I would like to show you the process to create an energy simulation in topologicpy using openstudio and EnergyPlus. This was one of the early implementations in the original topologic, and then for a while, perhaps it was a bit ignored, a bit left to kind of start not working correctly. And now with the new version of topologicpy that was just released today as the recording of this video, I debugged the whole process, made sure all the errors are corrected, and we're back to being able to create an energy simulation. There is a Jupyter notebook. This is what you see here on the screen is the last step in that Jupyter notebook. This Jupyter notebook is on GitHub and it's called energymodel.ipynb. And in this video, I'm going to go through it step by step and show you what are the needed requirements and how to conduct energy analysis. So let's get started. So first things first, I'm going to clear all the output here in the Jupyter notebook. And then I'm going to scroll all the way to the beginning of this file to get started. I tried to annotate it so that you can follow along, and I will explain all the code that's in here. As usual, the very first cell that I have here where I append the path to topologicpy, you don't need to run this cell on your own computer if you have pip installed topologicpy. This is because I'm using my developer machine, so you don't need that. But for me, I need to run it. The first step usually is to import the needed classes. As you can see here, some of them are not needed, like vertex and color. They were just here. It doesn't hurt to have them. But these are the classes that we're going to import. So this is done. I tried to put a print done at every cell so that you know when it's done, because some cells take a little bit of time to finish, like the ones where you are actually conducting the energy simulation. The next step is really important because you do need to have the correct versions of the software. So let's talk about this for a little bit. This workflow, as it says here, was designed and verified to work with Python 3.11, topologicpy 0.8.54 as the date of this recording, but it probably by the time you use this, I might have updated it, but it should still work. But you at least need .54. And I'm using openstudio SDK 3.10.0. This version of openstudio you can only download from GitHub. If you go to the openstudio.net website, you will not find it. You need to go to GitHub and download the latest release as of the date today, which is the 31st of August 2025. So just make sure that you have 0.8.54 for topologicpy and 3.10.0 for openstudio. When you download the openstudio application, so there is an openstudio application, and then there is the openstudio software development kit, the SDK, which is the Python binding for the openstudio software. The openstudio application, the latest one, says that it is using the openstudio SDK 3.10. However, if you try to go and download the SDK, it will tell you 3.9 is the latest one. So you need to go to GitHub and download the 3.10. All right? So this is very important for you to run this one and to check that you have the correct versions. So it says this workflow was designed and verified to work with Python 3.11, topologicpy 0.8.54, and openstudio SDK 3.10.0. And it tells you which Python version you're using. In this case, I'm using 3.11.9, so that checks out. I'm using topologicpy version 0.8.54, so that is also correct. And I'm using openstudio SDK version 3.10.0. In addition to just printing these things, I check against PyPy or PyPy or whatever they call it. So I have helper.version now has an additional parameter called check equals true. And if you do that, not only does it print the version number, it actually checks it against the version on PyPy. And in this case, it says that 0.8.54 is equal to the latest version. as well as the OpenStudio SDK version that you are using is equal to the latest version. Okay. Now, before we move forward, let me show you where to get 3.10, OpenStudio 3.10, and where to install it, and then to actually specify the path to it. So let's go ahead and open a web browser. And let's go to GitHub, and let's go to github.com/OpenStudio. Sorry, I think it is NREL, not OpenStudio. Yep. And we can go to OpenStudio here. And you'll notice under releases on the right side, releases 145 releases, that version 3.10.0 is the latest. So you click on that. It was published June 2025. And if you scroll to the bottom, you'll find all the artifacts or the assets, as they call them, that you can download. You can download for your own computer, whether you're using Linux or Darwin if you're using a Mac OS, or I'm on a Windows machine, so I would download this one and run it to install the software. Usually, and I'm just going to assume you have a Windows machine for now, of course, customize it for your own OS, but on Windows, it will install it under the C drive. So if I go to my C drive, you'll notice that I have OpenStudio 3.10.0. Okay, so this, you need to know this path, and under OpenStudio 3.10.0, you'll find a folder called bin, and under that, you can find the OpenStudio executable, the .exe file, and that's the path that we need. So basically, you can go here and say copy as path, and you can put it in your Jupyter notebook, which we will talk about next. So just realize that we have a difference between the SDK and the OpenStudio application, which is, in this case, it is 1.10.0, and it uses also the SDK 3.10. I hope this was clear. I hope I didn't make a mess out of it, but I hope you know what you're doing with that. So now we need to point it to all the paths, and it's really important to get these paths correct. All right. I have, with topologicpy, we have included example weather files, example design day files, example template OpenStudio models for the type of constructions, types of walls, etc. So you can use those, but obviously you're using defaults, and it might not match your project that you're trying to simulate if it's not in London, for example, because all of these files are based on London Gatwick Airport. So you need to specify where your EPW file is, the weather file path, and in my case, it's at this location, and the design file path, which goes along with your EPW file. And then you need to define that OS binary path. This is the one that I just showed you before, which is under OpenStudio 3.10, under bin, and it's this one. This is the file that you need to include here. So you put that in here. And then the next thing you need to be careful about is where to output the simulations. So I have created a folder called Energy Models under my desktop. So let me show you that. So under the desktop, there is a file called, or a folder, excuse me, called Energy Models. And topologicpy will automatically add a timestamp, and it will include the simulations in there. So you can see I have already 4 simulations. This is the latest one. And as you can see here, I have the OSM file, the runs, the reports, everything is in here that you can explore manually if you would like. So this is the usual report files that you can see, the HTML file. Okay, so this folder, Energy Models, need to exist. If it doesn't exist, it will give you an error. Okay, so make sure you create a folder, an empty folder somewhere, and you copy the path, and you put that under your output folder here. Okay. The next thing is that we need now, in this case, we are loading a brep. So now your geometry has to come from somewhere. If you have created it inside Jupyter Notebook, that's fine. You can just simply give that cell complex to EnergyPlus. So I just mentioned cell complex. Let me make sure everybody understands this. Building an energy model requires a building, and this building in topologicpy needs to be a cell complex, a set of cells where every cell is a thermal zone or thermal space already. And then you can optionally give it also a cluster of faces, just topologic faces, make a cluster out of them, and those can be your shading faces. So either neighboring buildings, let's say, you can just simply take every building and convert it into its faces. Like probably you should do like simple boxes, simple prisms, and take every face and make a cluster. Or this could also be shading devices that you put on the outside of the building, as you can see in this example. Whatever it is, you can just simply aggregate all these faces into a cluster, so cluster.by topologies, and you can put all these shading faces into one. In this case, I have them all saved as a brep file, and those are also included on GitHub or when you download, so you can download them from GitHub under the assets /energy model folder. Finally, and this is again very important, is your template file, your OSM template file. So you can make your own. And you should probably, if you're doing correct work, like something for a real project, you should make your own template that has the correct constructions for exterior walls, interior walls, slabs, floors, ceilings, whatever it is. You need to create your OSM template. I have given you a generic template that has reasonable material and constructions for an office building. So we're assuming that we are designing an office building here, not a residential. So if you're doing anything else, like a hospital or anything else, you have to start from an empty template. You can use the openstudio application to create that template without geometry. Just this template does not have geometry. It's just the materials, the constructions and their U values and all of that. The site and all of that. So in this case, we're going to go with OSM template -office building, and the version is 3.10. So make sure your OSM template format or version number matches the version of OpenStudio that you're using. In this case, we're standardizing on the latest version, which is 3.10. So as you can see here. So we run this, and it says done. We have specified all of these paths. So now we are going to load the geometry and set it correctly with windows, with external windows and shading devices. So the first thing is the building. So we say topology by brep path. So we're loading it from a path. This could come, as I said, it can come from anywhere. You could model it right here, in Jupyter Notebook and make a cell complex. But basically, this building is a cell complex. Now we need to add the apertures, and I'm doing it more algorithmically. So I am taking a glazing ratio. In this case, the glazing ratio is 25%. And I am taking the outsides or the exterior surfaces, the exterior vertical walls. So as you can see here, external vertical faces. These are the walls. And for every wall, that external and vertical, I'm creating a window. And I'm creating the window by scaling the wall by math.square root of the glazing ratio in order to get the correct area. Okay, so you take the glazing ratio, you do the square root of it, and you give that as the x scale, y scale, z scale, and you get an aperture face. And that you just save that face for now. When you're done collecting all your windows, obviously these windows could have also come from something that has been modeled previously, and you saved it as a brep file, as a cluster, and you take the faces and you just add them as a set of faces. That's completely up to you. Then you need to apply those apertures or windows to the cell complex, and we have a method called topology.addApertures. You give it the cell complex, which in this case called building. You give it the list of faces, in this case called apertures, and it will automatically find which aperture fits on what face in this building, and it will apply it correctly for you. All right. And you have to specify that the subtopology type is equal to face. You don't want to apply the apertures to edges or to the cells. You want to apply them to faces. So you specify that the subtopology type is equal to face. When you do that, it will automatically match the windows to the faces, and it will return the original building, the cell complex, with these faces already embedded in there. You don't have to worry about them anymore. They are already in there. Next, we get the shading surfaces, and this is just simply a cluster of faces from this brep file. So we have. And then we display the result just to make sure we have everything there. Just remember that if you just draw the building by itself, you will not see the apertures. A lot of people tell me, oh, where did the windows go? They are in there, but topology.show does not automatically ask the cell complex to give it its apertures and show them. So we're just simply displaying them by themselves here, but they are embedded in there. So let's go ahead and see the result here. Here is this building. As you can see, it's a very simple building with a central kind of atrium and 4 zones on every floor, and it has these shading surfaces, these louvers or whatever you want to call them, and the windows on every exterior face. Just an example building to work with. Okay, so now comes the interesting part. We need to create an energy model. And this, if you don't have everything set up correctly, this is probably where you're going to get a failure. This should not be here, so I was debugging, so I'm gonna remove this and this one, this line. I'll try to remove it from GitHub, but just ignore that. Okay, so to create the OSM model, we say energy model.byTopology, and please look at the documentation of that method because it has several input variables, but we're just focusing on the ones that will matter here. So building is equal to building. This is the cell complex. The shading surfaces are a cluster of faces. This needs to be a cluster, a topologicpy cluster. So that's shading surfaces. The OSM model path, which we specified earlier, the weather file path, which we specified earlier, the design day file path, same, and the glazing ratio is 0.25. I could have put here GR, which is exactly 0.25. This has to match, of course, because you don't want to draw windows that are at 0.25 and then all of a sudden you're using a different glazing ratio here. In any case, in reality, behind the scenes, it probably will ignore that if it finds apertures, and it will use the apertures area. But for any wall that does not have a window, it will use this glazing ratio. So be careful about that. If you want blind walls that don't have windows and you have already specified apertures, then you should make that a 0 here so that it does not automatically add a window to that wall. So we create this model, and hopefully for you it will work. You should see something like this. It will say this is a snippet of the OSM model. It's the top 900 characters of it. Just to verify that it worked, you'll notice that it will tell you the version number of this OSM file. This should say 3.10.0. And the OS building, the first thing is a building, and it should say topologic building because that's the default name for it, and it should be a commercial building as well. So you see that if this looks correct, then we are okay. We can move on to the next step. Now this next step here I've commented out is optional. You can export now this OSM file. You can export a GBXML file here and move to a different piece of software. You can move to Ladybug, Honeybee to do your work there with the GBXML, let's say. But in any case, we're commenting this out. We're going to actually run the simulation right now. So we do energy model.run. We give it the model. We give it the weather file, the OS binary file, and the output folder. So now it's going to timestamp that and save it. And this will take a little bit of time. So we'll just wait for it. Now this progress bar is supposed to work, but sometimes it will go from like 0 to 100% immediately and you will not see anything. I'm not sure why, but it doesn't matter. It is actually working and simulating, doing an annual simulation, hourly, I think. Here, well, it's done. It only took 20 seconds. It's a simple building. And if you go to the files, you'll notice there is a new timestamp folder that has all the reports in it. Great. So you could go and visualize it there or load it into the OpenStudio application, or you can do that also here and see it inside topologicpy in a nice kind of color-coded way. So here we're getting the space names that were used in the energy model and matching them to the original cells. So we're looking for something called topologic_name, and we're looking for that name underscore thermal zone. And we are trying to get all of that so that we can match the values to them. Okay, so this is done. So now we are going to get the report table column names to retrieve from the SQL data. So we're getting the HVAC sizing summary for the entire facility, and we are getting the zone sensible cooling or the heating or time not comfortable based on simple ASHRAE, whatever you want. And we're getting the column name that's called user design load in the first two cases, and summer or winter clothes in the case of time not comfortable. And in terms of the units, they are in watts. For the first, for cooling and for heating, they are in watts, but for the time not comfortable, of course, it's in hours. So you can choose the report. Which one do you want, 0, 1, or 2? Basically, do you want the sensible cooling, do you want the sensible heating, or do you want the time not comfortable? So 0, 1, or 2. So we can change that in a little bit to get the information. And then we get the report name, the report for string, the table name, the column name, and the units of that index that we specified here. And we send them to energymodel.query, and we give it the model, and we give it all these inputs, and we get those values. Okay, so that's done. And then we apply those values to the bottom faces of each space or cell. Okay, so we want to visualize the cells, but we don't want to color all the faces. We just want to color the floor of every cell. So this method here is for that. I won't go into the details here, but take a look at it. It's just getting the bottom faces and applying the dictionary to them, the dictionary value, and just creating a new cluster of colored faces. It will take a while because transfer dictionaries by selectors is a little bit slow. It has not, I tried to make it as fast as possible, but it's trying to match every face to every other face. Let it run. Okay, it's done. It took 45 seconds. And then we create a plotly figure to see the result. And here is the result. As you can see, nicely colored. This is the south where the shading devices are. Is the south north is there, so again, of course, it's cooler. Yeah, that's what it is. I hope you enjoyed this video, and please get in touch if you use it on a real project and you would like to have a chat with me about it. Would be happy to talk to you about it. Thanks.